Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Today's video will focus back on surface areas, but new solids here today, the pyramids and the cones. Now, I guess I made a little fib in saying that I was going to do separate videos for these, but after realizing that the book decided to do the same section for these ones and they merged some composite solids together, it's only fair to do it. The video may be longer based on the examples that we have, but I will save you a little bit of time by trying not giving you the origin in how these formulas come to be. I know people often don't care, even my students don't, but I got to give them a trusting process in how they can get it on their own, what it means when they're saying it, why it is they're doing it, and especially how it ties into the net drawings. You won't get that luxury, but I will be still giving you the idea of how you would make net drawings in case you ever want to do some of these practically, and just what the basic concept of that is. But I want to give you the formula straight up and what these things will be. So we are going to be doing some practice problems here. Before that, I left some blank space to be able to give you the concept of a net drawing of a pyramid and give you the surface area as a result, and then the net drawing of a cone, give you the surface area as a result. We'll do pyramid problems first, cone problems second, composite solids after all those, and then I think that they merge the pyramids and cones with even cylinders and prisms. So let's start off with a pyramid here, and I'm going to draw a square pyramid to start, something of that ilk. I do want to list out some features of this thing and talk about what's going on. So within this here, guys, when we unfold into the net drawing a pyramid, we instead of, remember the prism had two bases, so they were made by rectangles. We would unfold the rectangles together, put base on top and bottom. Here there's only one base, and we don't have rectangular lateral faces. Now we have triangles. This one makes a little bit more sense to unfold it kind of in a flowery fashion here. Get those kind of unfolding there. They are triangles after all. They go like that. And then you can get some measurements out of this. Now, when we talked about volume of pyramids, we had the altitudinal height, the height that went perpendicularly down to the base in the 3D way, something where that height isn't even an actual, it's like a rope that goes in the middle of a temple or whatever when you're doing it. This surface area doesn't have anything to do with that height. That's invisible for our sake. Everything here is on the surface. There is another kind of height we'll be referring to, which is the height of the triangle. Now on this surface, that height is represented, say, right here. On a slant, it goes down perpendicularly, but not to the base figure, to a base edge. So that height right there looks like that guy. And this is what we call a slant height. I'm going to put a lowercase l, I'm going to cursive it. That's called a slant height. So when I use L, we're referring to not the altitudinal height of the pyramid, but the slant height of the pyramid. And they are two different things, and we'll be using L in this case and not H for those. Okay? So that's important. When we talked about surface area of prisms, we were referring to perimeter of base. That will be included with this as well, and we will be referring to lateral areas of these things here. So to kind of keep this short here, the base is in this case the square, but it is it's the bottom of the pyramid. The lateral area is the result of adding together all of your lateral faces, in this case the triangles. That represents the lateral area. Your surface area is the addition of all five of these faces together. So your surface area formula is the lateral area plus the area of your one base, not two bases there. Now the part that I would generally get a deep dive into here, that I'm just going to go ahead and get straight into for you, and just give you the formula, no deep dive, say how to get the lateral area in one quick formula and calculation. It's done like this. The lateral area is 1/2 the perimeter of your base times the slant height. And I promise you there's a reason behind it in formula, and the reason behind the formula that you can kind of derive and such. Just not something we get to really get into today. Not the fun of it, unfortunately. Because if I do that, I'll have to do the cone one too, the formula behind that, and it gets a little tricky. All right, so that's the one for a pyramid. I'll just put PYR there when we do lateral area. And there is that. All right. Let me give you, I'll give you the cone one after. We'll do some pyramid problems, and then we'll get to the cone one after that. I'll reserve that space here. I'll write it here, and then we'll use it later. Let's start with some pyramids here. Of course, as the book wants to, it's going to give you a more complex problem first when we have to do the surface area based on, the area of a base that is a 1, 2, 3, 4, 5 6-sided shape. By the way, I gotta get my calculator out for this one. Give me one moment. Handy dandy calculator. Let's pop this guy up. Great. And if you saw one of my videos before, guys, to find the area of any regular polygon, in this case, oh, I have a hexagon shape. Hang on. In this case, a hexagon such as this one right here, what they do give you is it's a regular hexagon, as all these are 8 centimeters here. So they give you every side length here, 8 centimeters, blah, blah, blah. And then they also give you the length of what's called the apothem. I've mentioned this in the past in another video. And that's going to be 6.93 centimeters. Of course, they approximate it. I'm not a fan of that. That's the apothem. Starts with an A. The overall area of this base here, the area of that is 1/2 apothem times perimeter. So the apothem here is 6.93. And the perimeter is going to be 8 plus 8 plus 8 plus 8 plus 8 plus 8. 8 times 6 is the perimeter, and that's 48. So I'm going to take that one. Half of 48 is 24, and 24 times 6.93 is 166.32. 166.32 square centimeters. I'm going to leave that in my back pocket as we now find the lateral area. Now, good news-ish is, and I probably should have written this before here, that was perimeter of our base. Remember that 8 there? I actually used that somewhere here. I'm going to use that as well when we talk about the lateral area of this thing. The lateral area is 1/2 perimeter times slant height. Now the perimeter is 48. We already got that number. It's not hard to get again. I just mean when you use it once, just recall and substitute back in. The slant height, let me write this, perimeter is 48, and the slant height is marked right here. That's 12 centimeters. So when doing that formula there, the lateral area will be 1/2 perimeter times slant height there. Half of 48, again, is 24. 24 times 12 is double. 12 times 12 is 288. So the lateral area is 288 square centimeters. I said square centimeters, and there's no C there. Square centimeters, like that. And the surface area, it's not LA plus 2B, it's just LA plus B, 1B, right? Only a single base in pyramids. So we have the lateral area of 288 square centimeters. We have the base area of 166.32 square centimeters. And when we add those up, I don't want to mess this up. I'm going to say it's 454.32, but let's see. 288 plus 166.32. 454.32. So 454.32 square centimeters there. And, you know, it's very possible that in some problems in the future here, especially when I dive into some mixed review, we'll be getting the volume as well. So lateral area doesn't help you get that, but the area of the base that we found there, obviously 1/3 area of base times height, altitudinal height, something that we don't have in the problem right there. You could get if you work hard enough on it, but it involves trigonometry and stuff. We're not going to do that. Anyway, actually, would it? No, you can use Pythagorean Theorem. You can get it. But anyway, we're not doing that here. Not calculating the volume, just surface area. There it is. Good to go. Moving on. That was probably a harder problem than the ones we're going to do here. Not necessarily. I take that back. We actually now have, this is where Pythagorean Theorem comes into play. Now we're pointing at here, that 15 feet, that really looks, I don't know what they're pointing at. It looks like they're pointing at, you know what? I don't know, because this one looks like it's pointing right here. I sure hope they're not telling me this is 15, because I can't tell what that is. I'm guessing they're saying this is 15 right here. So the altitudinal height is 15 feet. I'm going to keep that there. And then we need to find slant height, guys. This altitudinal height will not be in our formula itself for solving the problem, but slant height will. So what are we going to have to do?
Well, let me tell you.
What we're going to have to do here is draw a right triangle out from this and find L using Pythagorean Theorem. Now, what length are we playing with right there with Pythagorean Theorem? Right here. Well, we got a full length of 16. We have to fall under some understanding, guys, that this is a square and that this is a center of that. So basically, it's going right down the middle. This is going to be half of that. This is 8 feet. It's hard to call that an assumption unless they call these regular pyramids they don't. So it's kind of hard to play under that assumption dearly, I know, but they wouldn't be finding surface area with the 1/2 PL kind of formula and stuff if these weren't regular bases. We're not even going to be dealing with rectangles. These are all regular polygons, equilateral triangles, squares, regular pentagons, hexagons, things like that. So anyway, that center, the height's going right down the center, and this is 8 right there. So we have 8 and 15 right here. I already know this number 17. This is a Pythagorean triple, but here we go. 8 squared plus 15 squared equals L squared. L being the slant height, L being the hypotenuse of this right triangle here. 64 plus 225 equals L squared. L squared is 289, and when we take the square root of both sides, we get L equals 17. That's 17 centimeters, and that is our slant height right there. Perfect. I'm not going to make the net drawing here. What we need is the area of the base. We need the slant height. Let's get both of those pronto. So the area of the base here in a square, we have 16 by 16, or 16 squared. That's going to be 256. Oh, I put centimeters here. I'm sorry, these are feet. These are 256 square feet here. There we go. And then the lateral area is going to be 1/2 the perimeter times the slant height. The perimeter is 16 times 4, because there are 4 16s there. The slant height is what we found here, 17. So we got to do 16 times 4 times 17, all divided by 2. Let me just calculate that one here. Looks like we're going to be getting 544. So the lateral area is 544 square feet. So your surface area in total is going to be your lateral area plus your base area. Ooh, that looks like a clean number. I think this becomes 800 even. So 800 square feet for that square pyramid. Okay. Another square pyramid here, and it's very, very, very samey on number 6 here. We are indeed finding the slant height by having the actual altitudinal height and dividing the 6 by 2 to get 3. That is 4. If you know anything about your Pythagorean triples, this will be a 3, 4, 5 right triangle. But let's use Pythagorean theorem there. 3 squared plus 4 squared equals L squared. 9 plus 16 equals 25. Oh, skip. It does equal 25. 9 plus 16 equals L squared. L squared equals 25, and when you take the square root of both sides, you get a slant height of 5 feet. So yeah, this is no different from that problem in the sense of what it is that we're doing. So got a slant height of 5 feet. A perimeter. Why don't I get perimeter for you first here? Perimeter is 6 times 4, because 4 sides. 6 times 6 times 6 times 6 is 24 feet. All right, let's get the area of your base. That's going to be 6 times 6, 6 squared, which is 36 square feet. Your lateral area is 1/2 your perimeter of your base, 24, times your slant height, which is 5. 20, I have 24 is 12, times 5 is 60. So your lateral area is 60 square feet. So the surface area will be adding the lateral area plus area of base. Again, these aren't really changing very much, only it just depends on what you're doing in the problem. So lateral area plus area of base, and that is 96 square feet. All right. Number 7, and this is our last, before we hit cones and composite figures, this is our last regular pyramid. And then we'll dive into some of the cone stuff. So this is, I don't know if you can tell what the shape is looking like here. I guess we're looking at the top. Well, I guess we're looking at the bottom. I guess this is underneath. It doesn't matter. We're looking at a pyramid. It's a triangular pyramid. It's an equilateral triangle. You know, what are we looking at here? It's not an equilateral triangle. What are we looking at here? Okay. Okay, I'm sorry. I see the drawing, what it is now. Sorry about that. I was thinking this was the triangular base. It's not. This is the triangular base right here. So this, right there. So this is the triangular base, and then this is the apex where all 3 sides, so these 3 sides are meeting to the top like that. So the 25 is one of the triangular edges. So if I make the net drawing for this, this is what I believe I'm seeing. I believe I'm seeing 40 centimeters all the way around. They wouldn't mark only just one of them and not let you know that the others were or were not that. So 40 centimeters all the way around the triangular base. This is your base. And then we have 3 triangles making the rest of your pyramid. 1, 2, 3. And then the 25 is one of these edges here, 25 centimeters going up any one of those for that part. Okay, so that's kind of what's happening there. Now, this one becomes interesting in several forms because the area of the base, we need to get a height for this thing that's got to be, one of those guys right there. There's a way of doing it trigonometrically. There's a way of doing it with Pythagorean Theorem. I'm going to assume you don't know the trig yet, so we'll be doing Pythagorean Theorem on that. And then we got to do Pythagorean Theorem to get slant height right here as well. So we got to get that. We got to get that. There's some work to do on this problem here. And I'm going to assume that that's how this problem is being generated. I'm trying to think if that's a fair way of going about it. I keep thinking this problem. I'm trying to think if that's a possible. Okay, yeah. Okay, yeah. Okay, here we go. All right. Hopefully you can make sense of the drawing stuff, because area of base, what we're going to do here, guys, area of base needs to be 1/2 base times height, because that's how triangles work, right? 1/2 base times height. Now I can establish my base as 40, like this length right here. Height needs to be perpendicular, though. So what are we doing within that triangle? Let's go and make kind of a bigger version of that. I have 40 centimeters here. I have a height that I need to find right here, knowing that this is also technically 40 right there. Now, I know the answer because of the way that Pythagorean special right triangles work and trig works here. But we're going to get an irrational answer here. So we ought to use Pythagorean Theorem. How so? We got to kind of construct a right triangle out of it like this. Now, because it's an equilateral triangle, this altitude had bisected this 40. This becomes here 20. So we have 20 squared plus h squared equals 40 squared. That's what we're going to be setting up here to find h. So 20 squared plus h squared equals 40 squared is our setup here. Okay. 20 squared is 400. H squared, and then 400 squared is 1600 there. H squared equals, subtract 400 is 1200. And then the square root of h squared is h, and then you get the square root of 1200 here. It's not an exact number, so I do not want you to round early. If you know how to simplify radicals, that's also, what did I say? I said I knew what this was. It's 20 times the square root of 3. You can also write, what is this, centimeters? This is also 20 times the square root of 3, 20 root 3 centimeters there. If you know anything about that, that's great. I think for the sake of this, for those who don't, I'm going to use the square root of 1200, and we'll be fine. Right, we'll be set with that. So, square root of 1200 centimeters, it's around, I don't know. Probably around 34, something like that. But I don't know. Sorry, 34. I don't know for sure. Anyway, so there's our height as an exact number. So your area of base is 1/2 base times height. So as an exact answer for now, this will be 20 times the square root of 1200. Gee, now I kind of wish it was 20 root 3, so we could turn it into 400 root 3. That would be fun. Anyway, this is in square centimeters. Once again, I'm going to leave this thing exact for now. Slant height, on the other hand, we once again have to use Pythagorean Theorem. And this one, thankfully, looks like it's going to be an integer value. So in this slant height principle right here, we have once again another triangle, but this time we have 25 going on. And then this 40 gets broken into 20 right there. So we have 20 with 25 and this unknown slant height. So that's 20 squared plus L squared equals 25 squared. Like that. Okay. 20 squared is 400. And here we have 625. Subtract 400, we get 225, and the square root of that is exactly 15 centimeters, like that. So we have a slant height of 15. And I know this is a lot of work for this problem. There's quite a bit to dive into with this one. Slant height's 15 centimeters, so your, what are we looking for? Lateral area. Your lateral area is 1/2 your perimeter. That's 40 times 3, so that's 120, times your slant height of 15. So half of 120 is 60. 60 times 15 is 900. 900. So we get 900 square centimeters there. So the total surface area here will be that lateral area of 900 plus 20 times the square root of 1200. There were other ways to simplify that you could write 400 times the square root of 3. But the end goal is I now get to calculate and approximate. I can now do my rounding and feel kind of comfortable with it. So I'm going to go ahead and do that right now. And we're going to get, oh, whoops, I didn't type the square root button. Here I'm going to get, what is that, 1200? 1592.8 if we round to the nearest tenth. So 1592.8 square centimeters. And I don't know if that's like the answer in the back here. I'm going to pause this thing. I'll look at the teacher edition. I think I have it somewhere. And I want to see if that's the answer. Not because I think I miscalculated. I want to see if that's what the diagram meant. That's what they were actually kind of talking about for this problem. So let me pause this. I'll come back to you. Okay, best of news, that was the breakdown of this problem. It is 1592.8. Now, the thing I should have, you guys probably have done trig running into this time. I started thinking about it. This is integrated math 3. So in integrated math 2, we ended on special right triangles. We ended on trig. So instead of Pythagorean theorem, you may, if you know something about equilateral triangles, if you know that these are all 60 degrees, you can work off a 30, 60, 90 triangle and use trig. But Pythagorean theorem is totally adequate. If you don't mind, I'm going to probably be using more Pythagorean theorem than not, because a lot of times we have to. Excuse me. Okay, let's start dealing with the cones here. In order for me to do the cone stuff, I'm going to have to get you what that kind of formula stuff looks like, because it's a little bit different. It does involve slant heights, but because it's a circle and you don't have triangles unfolding from it, there's kind of a different format from it, and it looks like this right here. When you have a cone, a cone is like a party hat. Only this party hat's going to have a circular base as well. So on top of the actual lateral face right here, the whole cone thing, there's also the base. If you've ever unfolded a party hat, the top part, I have the hiccups, I might have to pause this again in a second. The top part unfolds to just a big sector like this. It's like, wee, like that. It's actually a portion of a larger circle, basically. I cannot draw the circle well. It's basically a portion of a little better, of a larger circle. But that's kind of what happens there. Now, the slant height is still perpendicular there to the base edge like that. So the slant height is drawn anywhere on this thing, whether it's there or whether it's just plain on the edge. Okay, so slant height's a part of this portion. So when we use slant height, that's kind of, we bring it up. It's a part of it. Now, there's also the circular base right there. So however you want to draw it, it gets to maybe attach to that thing. Maybe it doesn't unfold with it, so to speak, but that is kind of a part of what's there, right? Now, the base is a circle, and that circle does have its own radius right there, this r, okay? This r like that. So just make sure that you're aware of that, because we still need to find, in surface area, there is the area of the base, and then, of course, there's the lateral area there. So there's no difference with regard to the surface area in a general format, surface area of a cone. It is still lateral area plus area of base. However, that lateral area is kind of a different calculation than just right here. And the base area is always specifically pi r squared. So we're going to get a more specific version of this that I will be using. Maybe, I don't know. Lateral area, again, I'm not going to dive into the reasoning behind it. It would take a moment. But the lateral area is pi times the radius of the base times the slant height of the cone. Pi RL. Pi RL. I like to call it, pi RL is pi RL. It looks like it says like pearl. Pi RL. Say it fast. That's the lateral area. And of course, the area of your base for these is pi r squared. So if you want a specific version of this, guys, the surface area of your cone is pi RL plus pi r squared. So there's a more specific version. Otherwise, you do lateral area plus area of base. So you might see me just do them kind of on their own, all depending on what I want to do with them. You'll probably actually see me do that more if I needed to find the volume of the cone as well. I think for now we'll just use pi RL plus pi r squared. And I'm fine with that. All right, so let's go ahead and dive into the cones, and let's do surface area of those. Now, slant height is represented. This is your slant height right here, 22 meters, because it's that slant from apex to edge of base there. that kind of draws right into that. And we also have the radius as well. So this is just, straight up radius, slant height. That's all we need, right? Because surface area, one more time, is pi r L plus pi r squared. We need r, we need L, and of course we need pi. Pi is a constant value though. So leave the answer in terms of pi, no problem. The surface area for this one is going to be pi times the radius times the slant height, that's your lateral area, plus pi r squared right there, that's the area of the base. So here we go. Surface area is 14 times 22. 308. 14 times 22. 308. So 308 pi. That was the first calculation I struggled with there. I know this one's 196 pi there. So that surface area in total is going to be 504 pi. This is in square meters. All right. That's number 8. Number 9, we once again have a slant height. This is of 23 right there. The diameter is 23. The radius is going to be half of that. So the radius is 23 over 2 centimeters. Now, a lot of you guys are probably trying to get that into decimal form right now. I would caution you, not caution you, but when I want to leave in terms of pi, I like my fraction answers best because that means for sure, exact answer and kind of nothing else with that. It's your call. It's your call. You'll get an exact answer regardless, but I'm going to leave it as 23 over 2. I'll give you the decimal version after, and you'll probably be satisfied with it. All right, here we go. So the surface area here is going to be pi RL, pi RL, L, plus pi R squared. Which means looks like we're going to have to get a common denominator here. I don't know 23 times 23. And we're going to have to do that twice. So let's see. 23 squared is 529. So this is 529 pi over 2. And this is 529 pi over 4. If you can imagine that. Because we square the 23, we square the 2. We get 529 over 4 times pi. So now we got to multiply this guy here by 2 over 2. This is probably where you're saying, I use the calculator for decimals. No. 1058 pi over 4 plus 529 pi over 4. And a best exact answer with regard to fractions here, 1058 plus 529 gives me 1587. So 1587 pi over 4 square centimeters. All right. As an exact answer, that's going to be, it'll have a 0.25. It'll be 0.75. So it's also 396.75 pi square centimeters. And I know most people are looking toward that second one saying, yeah, that's good. And you're not wrong. But when you end up dividing by 3 and you got to round it and they say leave in terms of pi, you're doing something wrong for yourself. So make sure you know how to work fractions as well. Be accepting of them. They have their functions and uses as well. All right. 2 more cones and then we got some composites. Let me see how many composites I want to play with here. Oh, whoops. Yeah, there are a lot of different ones. We're already about a half hour in. At some point I'm going to give up on the composites. Let's make sure we get some of the cones and see what we can do from there. Okay, we do need slant height. Oh, sorry, we have slant height. We do need radius here. So slant height is 25. If that's 25 and this is 25, right? The slant height right there. Or radius can also be drawn right here. How about that? It's also a right angle. The radius is all the way around. We need that r right there. Slant height's 25 and the altitudinal height's 24. So r squared plus 24 squared is 25 squared. I know this one's going to be 7. That's a 7, 24, 25. Pythagorean triple. 576, I think. 576 is 625. R squared, subtract that. That's going to be 49. Yep, 49. And then we get R is 7. So 7 inches for radius. So we got R is 7. We got slant height is 25. Let's go to work. The area of the base, well, we don't have to say all that. Surface area is pi RL plus pi R squared. Pi RL plus pi r squared. So that'll give us a surface area of 7 quarters is $1.75. So 175 pi plus 49 pi, and that's going to be 224 pi square inches. So Pythagorean theorem to get the radius there, and we are good to go. All right, now this time it looks like we got to use Pythagorean theorem to get slant height, and in this particular instance here, we need to make sure we know that the r is 24 over 2, which is 12 inches. We could also write that, maybe right here, 12 inches. And Pythagorean theorem with this, right triangle, if you will, we need to get that slant height right there. This doesn't look like it's a Pythagorean triple that I'm aware of. So this slant height might be not a perfect square, which is one of those things we can't approximate it if it's not. So we got 12 squared plus 35 squared equals L squared. 35 squared, 1225? I think it is. I'm not for sure. Let's see. 35 squared, 1225, yeah, plus 1225. And I am going to go to the calculator to see if it is a perfect square when we do all this. We just add them up right now as we're doing this. Plus 144, we're going to get 1369. So is there a square root of that? Is that a perfect square? Oh, it is. It is. All right. It's a larger Pythagorean triple that I wasn't aware of. So L squared equals 1369. And you take the square root of it, you do get exactly 37. So you get 37 inches. That's your slant height. Your radius was 12. And then we can go to the formula for the rest of it. Pi RL plus pi r squared. So your surface area here will be pi times the radius times the slant height plus pi times the radius squared. Okay, 12 times 37, I believe, is 444. 12 times 37, 444. So 444 pi, and then plus this is 144 pi. That should be 588. So that's 588 pi. 588 pi, and that's square inches, like that. So that's it. We're good. They said leave in terms of pi, and we got that. So that's some stuff with cones there. All the rest that we have are composites, and you're going to have to know what I mentioned before with regard to when you subtract some things out. It seems, it says we're appropriate leave in terms of pi when necessary round to the nearest tenth. I don't know what that means. I don't know if that means we're supposed to leave in terms of pi or not. I have no idea there. But listen, I'm not going to do a bunch of composite solids. Let me break down a couple. I'll do 12 and 13. I don't know. That looks cool. It looks like a diamond. Just to save time for the hexagon stuff, I'm not going to do that. It's not that it takes, well, that might take a second to do. And inverted cones have no fun aspects to them with regard to, except for similarity. You can do slant height in a kind of a fast fashion there. I think I'm just going to do those two. I'm just going to do numbers 12 and 13 with you guys. So if you don't mind, two more composite solids. We'll play with the cylinder there again with surface area. And here we go. All right. I'm going to name these figures. I'm going to give them numbers. And here's figure 1. Here's figure 2. Let's find the surface areas of them separately there. In the surface areas of these, we need to make sure we know the slant heights, everything here. That is a square pyramid with 8 feet all around. So both of them do have a perimeter of 8 times 4, which is 32 feet. That's going to be important there. Different slant heights, though. Slant height for the first figure is 15 feet. Slant height for the second figure is 18 feet. What else will we need? Area of base. Okay, so that's all we'll kind of need. Oh, area of base for both of them is, now I'll let you know what. We're not going to end up needing the area of the bases, but that's okay. This is going to be 8 times 8, 8 squared, which is 64 square feet. Yeah, whether you want to talk about this now or later, the bases are covered. The bases are covered. Therefore, they're not a part of the surface. Really, all that counts are the lateral areas of both of these. All the triangles on the top pyramid, all the triangles on the bottom pyramid. That's all that counts. The bases are not a part of it. I think that's going to be the same thing for, I think, all these shapes that we're going to do, except for the inverted cones that you saw, which we're not going to do. Even these bases here won't count, so yeah, I'll just do that. We're just going to add the lateral areas of these. We don't even need areas of bases, so we don't need full surface area. Kind of sweet. So what's the lateral area of the first shape there? That's 1/2 perimeter, which is 32, times its slant height, which is 15. So 1/2 perimeter times slant height. Half of 32 is 16. 16 times 15 is 240. So this is going to be 240 square feet. The lateral area of the second guy here is 1/2, same perimeter, times its slant height of 18 feet here. Half of 32 is 16. 16 times 18 is 288. If I'm saying all that correctly. 288 square feet. Now the surface area, this is still technically called the surface area of the total, just we're not adding the bases within. It's not the combination of the two surface areas. It's really just these two things added together because the bases are covered, both of them. So it's the area 240 plus 288 there, which is going to be 528. So 528 square feet is the surface area of that whole thing, and you are set to jet, good to go. Whoa. Okay, number 13. How far? I'll do 15 with you as well, just because there's a prism. Okay. All right, number 13. These are, once again, slant heights of these cones. These are cones. That's a cylinder right there. We got a radius of 12. Do we have to use radius for any of this? Oh, we do for the cylinder right there. All right, we got 3 figures. They are not congruent on top and bottom. So I got figure 1, figure 2, figure 3. Let's start with the cones because that's in recent memory here. And remember, all that are considered are lateral areas. All bases are covered. The bottom of the cone, the top of the cylinder, the bottom of the cylinder, the top of the inverted cone, all covered. Surface area of the total is just the lateral areas of all 3. So the lateral area of the first guy here, of this cone, is just the pi RL. It's not the plus pi r squared. It's just the pi RL. So pi times the radius of the cone is 12 meters. Oh, I guess we do need the radius here as well. Times the slant height, pi RL, is 26, like that. So pi RL, I don't know, 12 times 26. I'm sure I could come up with it pretty fast, but it's all right. Don't want to mess up. Kind of bigger problem. So 312. So this is 312 pi square meters. Okay, that's the lateral area of the first guy. Lateral area of the third guy, that's another cone right there. Same thing regarding the radius. So pi r, and this L is 32. That's the slant height there. 12 times 32 gives us 384. So 384 pi square meters for that one. And then the the lateral area of the cone, if you guys remember, the cone unfolds, not the cone, the cylinder. The cylinder unfolds to a large rectangle whose height of the lateral faces is the cylinder height, which is 15, right? That's the, lateral area. So the height gets multiplied by the perimeter of the circle, otherwise known as the circumference, 2 pi r. So this is 2 pi r h. This is for a cylinder. So the lateral area of the cylinder of 2 is 2 pi, r is the radius, 12, times the height of, not 12, or not 2, it's 15. 15 here. Let's do 2 times 15 is 30, times 12 is 360. So that's 360 pi square meters. Okay, so our lateral areas all added together will give us the full surface area of this thing, LA1 plus LA2 plus LA3. So 312 pi plus 360 pi plus 384 pi. Don't want to mess that up. I'm kind of doing it in my head at the same time, but that's okay. 312 plus 384 plus 312 plus 360. So 1056 pi. So surface area is 1056 pi square meters. All right. There's that one. It's weird. It says when necessary, round to the nearest tenth. I don't know what that means. If you do want an approximation of that one, y'all, we are going to be getting, where's pi? Times pi here. That is 3317.5. So it's approximately 3,317.5 square meters there once I multiply pi with that guy. All right. All right, I'm going to do one more. Skipping this cone, skipping that. I love that one just because it's beautiful. I do want to know how much you got to do whatever. But let's just do one more here. Another version of the same kind of thing, only back to a pyramid. And we do have the, what are they marking as 9 here? Okay, that's that height right there. Oh, there's some work to be had for this one. All right, let's have some fun with this, number 15. So, we have the prism, this square. Oh, maybe it's a cube. Oh, it's a cube. Never mind. We don't have to have fun with it. I take it back. I thought we'd use Pythagorean Theorem to find this length. We don't. They're marking congruent marks. There's a congruent mark to that. That means if this is 9, so is that. So in the middle, guys, we do have a cube. Now, we're not finding the volume. We're not doing 9 times 9 times 9. You just got to know that everything around it is a 9. And I guess that's important for us just noting that there. So these are all 9s. That's important for the pyramids as well. So perimeter, all the bases are the same. I don't need the areas of the bases, but I do need the perimeters of the bases. The perimeters for all of these is 9 times 4. That's 36 centimeters, right? So perimeter all the way around that base, 9999, whether it's this prism or the pyramid, it's like that, okay? And they do give us slant heights for these. Let's call this figure 1, figure 2, and figure 3. The slant height of figure 1 is 15 centimeters. There is no, the height of figure 2 is 9 centimeters. For me, I'm calling this a height, the distance between, I'm calling that a base and that a base there. So the height of figure 2 is that, and the slant height of figure 3 is 19 centimeters. So let's find the lateral areas of our two pyramids here. Lateral area is 1/2 perimeter of base times slant height, and they're two different ones. So the lateral area of the first figure 1 here, 1/2 perimeter of base, what do we call it? 36 times a slant height of 15. Half 36 times 15. So 18 times 15, 270, I think. So 270 square centimeters. And remember, it's just the lateral area we need. Apparently, we don't need the base because it's covered, fully covered. And so is the prism bit as well. We'll get to the prism after this other slant height here. The slant height of the lateral area. The lateral area of the third object here is 1/2 perimeter of base, once again 36, times the slant height of 19. 18, if I knew 18 squared, I could tell you what 18 times 19 was. 18 squared might be 324. So I'm going to guess it's 342. So let's see if that's true or not. So 18 times 19, is it 342? It is. So 342 square centimeters for that one. That's 3. I'm saving the prism for last there. The prism, we are just doing the lateral area, the one like around these walls here, if you will. And that is perimeter of base times height. So perimeter of base is 36. The height of the prism itself is 9. 36 times 9 is 324. Yeah, 324 square centimeters. Hey, that's the same. It's 18 times 18. 324 square centimeters. So the surface area of all three of those, we got to add all three of those up. 270 plus 324 plus 342. Nope, no pi's within these, anything like that. Just got to add those up. 324 plus 342 plus 270, and we are getting a grand total of 936 square centimeters. Something I'd love to look up. I'm going to, because I don't want to make any mistakes. I'm going to go back and triple check, whatever, anything else. I want to see if my answers are correct. If I made a boo-boo, I'm going to go back and change it. And because I hate putting these videos up and saying, there's a big mistake. Of course, I should check beforehand and anything else. Otherwise, that will do it for this one. So let me pause and see where we're at. Okay, in a stroke of very great news, everything is correct. I will state in the very first problem that I did, if you were with me on it, number 4, they did say round to the nearest tenth if necessary. I would say, because I put 0.32 instead of just 0.3, almost in those cases, because it was an exact number, I'd say, nah. That's that. Like, I like to just cut it off when I have to, when the numbers run on. But Either way. So they're all correct. So I feel good on that, feel accomplished, because I don't want to make those mistakes with you all the time, and I apologize whenever I do that. All right, so that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. I sure hope that all this connected here. Take care. Till the next one.